Hello, in this video we're going to go through the basics of sample size calculation, the importance, as well as just a little bit of foundational knowledge on GPower. I also want to give credit to Dr. Mark Williamson. He is actually the person who came up with the majority of this information. I have to admit, I was looking for some good resources and I found this one, and I thought, you know what, I'm not going to reinvent the wheel. All right, so the why of sample size calculation. So in designing an experiment, a key question is how many animals? Normally we're going to talk about subjects, right? People, how many people do I need for my experiment? Too small of a sample size can underdetect the effect of interest in your experiment. Too large of a sample size may lead to unnecessary wasting of resources, and it wouldn't be animals, it would be people. So in one case, you might not get enough people, and you might actually be having an effect, but you just can't detect it because you don't have enough people, or you don't have enough maybe businesses, or whatever it is you're measuring there. You just don't have enough to detect whatever it is, whether it's a leadership component, a retention component, an anxiety, a stress, whatever it is, you can't detect it because you just don't have enough of a sample size. But yet, if you have too large of a sample size, you may end up wasting resources and businesses. So you might be going around, thinking, oh, I need more people, and you really don't. So similar to Goldilocks, we want our sample size to be just right. So the answer to this is a sample size calculation. Our goal is that we strive to have enough samples to reasonably detect an effect if it's really there without wasting limited resources on too many samples. So that's kind of the purpose behind it. So key bits of sample size calculation. So what are kind of the main players here that we're going to be talking about? The first is effect size, and that's the magnitude of the effect under the alternative hypothesis. So the larger the effect size, the easier it is to detect an effect and require fewer samples. Power is the probability of correctly rejecting the null hypothesis if it is false. So it's also known as just the probability of detecting a true difference when it exists. So you want that, right? Because you want to be able to detect a true difference when it exists. So power is really important. Power is equal to 1 minus beta, where beta is the probability of a type 2 error, which is a false negative. The higher the power, the more likely it is to detect an effect if it is present and the more samples needed. The standard setting for power is 0.8. Now, significance level is alpha, and that's the probability of falsely rejecting the null hypothesis even if it's true. So this is also known as just the probability of a type 1 error, which is a false positive. The lower the significance level, the more likely it is to avoid a false positive and the more samples needed. So normally what we set alpha to is that 0.05. So think of all the times, right, when we're getting our p-value and then testing it, is it greater than or is it less than or equal to? We are always testing it against our alpha, which is this 0.05, which is the probability of making a type 1 error. That's where that comes from. So given those 3 bits and other information based on the specific design, you can calculate sample size for most statistical tests. So not all, but most of them. So effect size in detail. So while power and significance level are usually set irrespective of the data, the effect size is a property of the sample data. So it's essentially a function of the difference between the means of the null and alternative hypotheses over the variation, which is our standard deviation in the data. So you can see that over in this formula where it says effect size, mean 1 minus mean 2 over the standard deviation. So you don't have to worry about that formula. That's just to make sure you kind of get a feel for what that means. So how do we estimate effect size? So one way is to use background information in the form of preliminary or trial data to get means and variation, and then calculate effect size directly. So that would be if for whatever reason you had like an initial survey, and then like if you were creating maybe a survey. So this information might come from that initial survey, and then you would have your next, your final round of your survey. And then you could use that information from your initial survey to help inform this one. You can also use background information in the form of similar studies to get means and variation, and then calculate effect size directly. So for that, the background information would be like when you do your lit review, you're kind of collecting information on what are kind of the norms, what are the standards when you're doing, maybe using that type of survey or doing that type of I really would be probably a survey or that type of experiment if it is an experiment. Ultimately, though, with no prior information, we would just make an estimated guess on the effect size expected or use an effect size that corresponds to the size of the effect. So broad effect size categories are small, medium, and large, and different statistical tests will have different values of each size for each category. So in most cases, and what we're going to be doing for this week is we're going to use the no prior information. So we're going to make an estimated guess on the effect size expected, or use an effect size that corresponds to the size of the effect. So that's what we're going to be using is C. So just, we call it statistical rules of the game, just a few pieces of terminology to refresh yourself, just so we're all, using the same information, right? The null hypothesis is the default or boring state. Your statistical test is run to either reject or fail to reject the null. We then have the alternative hypothesis, which is H1 or it's also HA, and it's the alternative state, usually what your experiment is interested in retaining over the null. So your alternative is normally kind of what you maybe hope is happening or what you think might be happening, and your null is just that default of they're equal, there's nothing happening, there's no relationship. A one-tailed test is looking for a deviation from the null in only one direction, so is a variable larger. In most cases, we don't do a one-tailed test. In fact, I don't think we've done one-tail on any of these things. In most cases, and I think pretty much everything we've done in this class, is a two-tailed test. And that's looking for a deviation from the null in either direction. So is variable y different from 0? Basically, the two-tailed is just we're looking for any kind of difference. So there's any kind of relationship, any kind of difference, any kind of change. Now, parametric data is approximately fits a normal distribution, and that's what's needed for many statistical tests. So often when we do those little checks before we look at our data, is to make sure that our data is parametric. Non-parametric data does not fit a normal distribution, so the alternative and less powerful tests available. So if we can, we always want to do the parametric data. We want to use parametric tests just because they are much stronger. But if we don't have data that fits a normal distribution, we will switch to non-parametric data, which is fine. There's nothing wrong with it. It's just a little less powerful. Also, paired dependent data categories are related to one another, often results of before and after situations. They could also be the same person measured, how big is my hand and how big is my foot. Well, I am the paired information, and it's my hand and my foot size. Unpaired or independent data categories are not related to one another. So that would be male versus female. That could be your test group and your non-test group. Dependent variables depend on other variables. The variable the experimenter cares about, also known as the Y or response variable, and the independent variable does not depend on other variables, usually set by the experimenter, also known as the X or predictor variable. So a little bit of just using GPower, and we're going to obviously dig into this a lot more. We've got the download for Mac or PC, and I do have a video that covers just the downloading, so check that one out. Or hopefully you already checked that out before you opened this one up. But if not, make sure you check that out so you can download GPower. There's also 3 basic steps. You select the appropriate test, you input the parameters, and so you would just pick what you want, and in most cases we're going to use the a priori. And then we're going to, input parameters down here, and then determine the effect size. So we would click there. Or if we aren't using that determine box, we would just click the calculate. For situations when you have some idea of parameters such as mean, standard deviation, I'll refer to this as having background information. So that's when you know the mean, the standard deviation of each group. If not, then we'll refer to it as a naive, which means we don't know, so we're just going to make our best guess for the information. A little bit about the GPower graphics. We're really not going to go into these in a lot of detail. I just wanted you to kind of understand it a little bit. So central and non-central distributions. So that's this first graph, which you can see you've got your two bell curves and you've got the two overlapping groups. So that shows the distribution of the null hypothesis, which is red, right? And that's saying that there's nothing going on, nothing's happening, no relationship, no difference. And then the alternative, which is our blue. And that's that something's happening, there is a relationship, there is a difference. It also has those critical values. So the X and Y plot are a range of values, and that's this one over to the far right. And this one can generate plots of one of the parameters, alpha, effect size, power, and sample size, depending on a range of values of the remaining parameters. So in general, we're really not using either one of these. This is just some people really enjoy this type of stuff, and they want to dig into it a little bit more. But for the sake of this course, I just wanted you to know, here it is, and here's what it does, but we will not be digging further into that. All right, so that ends this video, and stay tuned for the next one.